Hey everybody and welcome. And in this video on this fine Wednesday we are going to work through a integration problem and calculation. Specifically we are going to use integration by parts, which is a technique used for complicated integrals, ones that the U substitution would not work for. And so the example I want to use is another biomedicine example, and that is thermodilution. So we want to measure the cardiac output of somebody's heart. And this is important because if it falls below, let's say, 3 milliliters per minute, or 3 liters per minute, excuse me, then that patient is in critical condition. That patient could die, and it is very dangerous to have such a low cardiac output. The average or the normal cardiac output is around 5 liters per minute. And so techniques have been developed over the past couple hundred years for measuring this cardiac output. And one of them began in the 1970s called thermodilution, with the development of a particular catheter that would allow for this measurement technique to even be done. And so what would happen, and what physicians would do, is they would take a 2 balloon tip catheter, for example. They can use other types of catheters, but this is the one that is typically used now, I believe. And they can insert it through the jugular vein in the neck, or they could even go in through the arm. And they move this catheter all the way to the superior vena cava and through the right atrium. And then in there they can push through an injectant or solution, particularly cold saline or water or dextrose. And then they could use 2 thermistors right here, which is an image of one here, which would be in the pulmonary artery. Put that in here, which is this purple guy right here. And this thermistors are sensitive to temperature change. And so when we injected the cold water, the heart takes time to warm it up. But we want to know how long it takes to warm up. So we want to measure the rate of change of the temperature. And we can quantify this temperature change in a way that allows us to measure the amount of blood being pumped. And so the first thing we want to do, which can be tricky, this is probably the trickiest part of the entire example, and that is we want to quantify that cold solution we are pushing through the atrium. Quantify the cold. And it's tricky, not because it's a complicated calculation, but tricky because it's difficult to conceptualize quantifying temperature as a measurement of a flow, so the blood flow. So we want to quantify the cold. And so we can develop an equation. We'll call the main variable quantity N. So that is the quantity of our solution that we injected in the atrium. And we can set that equal to the volume of the injected times the change in temperature between the body and the temperature of the injected. And so this right here is quantifying our cold. We are quantifying temperature. And we can even give units to this equation. And those units would be, for the volume, so VI will be equal to milliliters. And the temperature of both the body and the injected, so BI, is equal to degrees Celsius. And so the quantity of cold is going to be equal to milliliters degrees Celsius. Milliliters degrees Celsius. And now we want to know the quantity out. So how much of the cold is left after a time period, after it moves through the heart, after it's pumped out, because that will give us the information we need to calculate the cardiac output. And so we'll give this a variable as well. Let's use a different color. We'll use green. So we have quantity out, how much quantity is out. And this is going to require an integral because we have a rate, we have change in t. In fact, let's write that as change in t. Change in t. So we have the integral, and we can go from time is 0 to infinity, which is cool, which is why this technique is deployed, is you can do it continuously. You can run this saline through, or dextrose, or whatever it is, you can run it through continuously and get frequent measurements. Whereas if you used previous techniques like a dye, which didn't dilute very well, you would have to frequently adjust what is being pushed through and reset everything, essentially. And so you would have to frequently make changes just to get a measurement. And so with this technique, you can just do it continuously over time, which is really useful as it reduces the amount of labor on physicians and nurses and who's ever working on the patient. So we have our improper integral from 0 to infinity of the flow rate F, times the change in temperature, dt, so over some time interval dt. And so we can use our integration properties, and we can actually just rewrite this as our flow rate times the integral of our change in temperature, dt. And so we can give units to this portion of this equation as well. And so change in temperature, again, is going to be equal to degrees Celsius. And our dt, so our time interval, is going to be in seconds. So basically our quantity out is going to be degrees Celsius seconds. We can build an equation using our two formulas. So we can use our quantity in and quantity out. We have written the quantity out as this guy. And so how would we combine these to get a formula for developing a cardiac output? Well, we just want to know the F. We want to know the flow rate. This is the cardiac output. And so we could set. So in order to develop this formula, we have to make an assumption, and that assumption is that nothing is leaking out of the blood vessels as it moves through the atrium and the pulmonary artery. In reality, a little bit does leak out, and you can control for that. It's not, and you can use factors to control for that, and those factors are empirical. So through experiment, they have developed values to control for it. We won't go through that here, just because we're just keeping it somewhat high level. And so we can actually set the quantity in equal to the quantity out, assuming there is no leakage. So we can set VI, let's write quantity in is equal to the quantity out. And so we are taking this guy right here and this guy and setting them equal to each other. But this does not tell us the cardiac output. This is our equation that we are going to use. To know the cardiac output, we need to solve for this F, as I said before. So we can rearrange the expression so that we divide by the integral. Because if these are equal to each other, let's just write it out. So VI TB minus temperature of the injected is equal to capital F integral 0 to infinity change in temperature over a small time interval dt. And so we could divide by the integral change in T dt to both sides. Change in T dt. And we get F, our cardiac output, is equal to VI, the volume of the injectant, the quantity of cold, divided by the integral from 0 to infinity, change in T, temperature, dt. And so here is our formulation for developing the cardiac output. And the units, the important part, the units for F, our cardiac output, milliliters degrees Celsius over degrees Celsius seconds. And guess what? Temperature crosses out, so the units actually are milliliters per second. And we can convert this to liters per minute if we were using actual values. So these are the units that we want to measure cardiac output, CO. Now typically this is done, so in real life this is done electronically or digitally using computers to calculate this. So it'll get the input parameters. The thermistor will measure the change in temperature. The catheter will have a measurement for the volume, and it will perform the integral calculation for the change in temperature in order to get the cardiac output in liters per minute. It'll even do the conversions for you. The wonders of technology. But for our purposes, we are actually going to go through an example as if we didn't have a computer. And so let's say we are given the volume of the injectant. So VI is equal to 10 milliliters. And let's say the body temperature is a normal body temperature of 37 degrees Celsius. And the temperature of the injectant is equal to 0 degrees Celsius. And so we would just plug these into the numerator. So 10 times 37 minus 0, which is just 37. So 10 times 37, which is 370. So this is going to be 370. And we could add in a constant, times it by something like 0.89 or some controlling constant for factors like leakage through the catheter as the injectant moves along the catheter. And so we won't do that, but you could do that. And I think in practice, you do actually have to do that. So we have 370 in the numerator, and that's milliliters degrees Celsius. Milliliters degrees Celsius. But we need to integrate this improper integral from 0 to infinity of change in T dt. And so we can use an equation for change of T. And we can use empirical data and the development of this curve here, which is what it typically looks like for the temperature change over time. And so you get like this huge bump with the cold injected first entering, and then it slowly gets warmer over time, or the temperature goes down. The temperature changes in the negative direction. And so we can use this curve, and I've identified the equation it represents. And so we can write that out as, we'll say change in T is equal to 0.1 times T squared times e to the negative 0.31 T. And there it is. That is our change in t. So now we need to integrate. From 0 to infinity of 0.1 t squared e to the negative 0.31 t dt. And now it doesn't look too overwhelming or intimidating as an equation, but it actually is quite involved when doing the calculation and will require integration by parts. This is going to require integration by parts because we can't easily use u substitution here. And anytime you see e raised to something, you will likely have to use e raised something multiplied by another something. You will probably, if u substitution doesn't work, you will use integration by parts. And so the derived formula that you probably learned in calculus is the integration by parts formula, and that is uv minus the integral of v du. And so we will be using this as our formula. And so you're probably like, well, what's u and v? Or v and d? Yep, so we have to identify those. And so we have 0.1 t squared, and we have an e to the negative 0.31 t. So which one do we want to make u and which one do we want to make v? Well, we need to find the derivative of u, so which one of these is easy to find the derivative of? Well, I would say probably this one. This one's a little bit easier. Well, it's a star. Well, it was meant to be a star. We want to make u equal to, let's do this in white. We're going to make u equal to 0.1 t squared. And so the derivative, if we take the derivative of both sides, we get du, which is right here, equal to 0.2 t. And so there's our du. And our v is going to be equal to e our dv is going to be equal to e to the negative 0.31 t. And if we integrate that, we get v is equal to negative e to the negative 0.31 t over negative 0.31. And really, this is just the antiderivative. We just took, this is the antiderivative. Antiderivative. This is the antiderivative of this. Oops, this is not supposed to be negative here, because I put the negative here. Really, all I did was move negative 0.31 to the denominator. And so you get negative 1 over 0.31 times e to the negative 0.31 t. Okay, so this is the v. So now, I'm going to erase this because I'm going to use this room space over here. Now we have to plug in our values. So if we plug in our u, we get 0.1 t squared times our v, which is negative e. You know what, we can write that as negative 1 over 0.31 e to the negative 0.31 t. So we're multiplying those together. And then we are subtracting the integral of negative e to the negative 0.31 over 0.31 times our du, which is 0.2 t dt. And so you can see how this might be getting complicated. Well, what we can do is we can easily combine this, or simplify, I should say. We can simplify this. We get 0.1 negative over 0.31 t squared times e to the negative 0.31 t. And then we can subtract this guy. Well, this is actually going to be negative times a negative. That's a positive. This is a scalar. This 0.2 is a scalar, so we actually move this out. So we get plus 0.2. And we can also got 1 over 0.31, which is another scalar. So we could move that out. Of the antiderivative from 0 to infinity of e to the negative 0.31 times t dt. And you might be wondering, what is the integral of this? Well, we have to apply our integration by parts again, so a second time, which is why I put this bar here. So in this case, we have t as one of our products, and then e to the negative 0.31 as one of our products, because I moved the scalars 0.2 and 0.31 out in front of the integral. So our u is equal to, we will set it equal to t, because we will have to find the derivative of it. So if we find the derivative of both sides, we get 1. And our dv will set equal again to e to the negative 0.31. And we get the antiderivative to once again be negative 1 over 0.31 times e to the negative 0.31. And so if we plug this in once again, we get negative 0.1 over 0.31 t squared times e to the negative 0.31 t plus the scalar in front of our integral, 0.2 over 0.31, and then our uv. So we're going to go boom, just like this. So our u is just t times v, which is a negative 1 over 0.31 e to the negative 0.31. Forgot the t. There's the t. Forgot the t. So 31 t. Those multiplied together minus our integral from 0 to infinity. Whoops. From 0 to 8 infinity of our v and du. So this, again, we can move this out. Negative 1 over 0.31 e to the negative 0.31 t times our du times 1 dt. And so here we go. Now if we write this out again, for the final time, we get negative 0.1 over 0.31 times a t squared times our e to the negative 0.31 t. That term plus our 0.2 times 0.31, and we're going to multiply that by t times negative 1 over 0.31. Let's give some space. .31 e to the negative 0.31 t and then we have plus again, so we'll move this out 1.31, and then we are left with e to the negative 0.31 t. The antiderivative of that is times a negative 1 over 0.31 times e to the negative 0.31 t times that one, which we don't care about. That. All of that plus the constant of integration, c. And so, I think that is it. This looks correct at least. I think I did that correctly. Here is this is the result of integrating 0.1 t squared e to the negative 0.31 t dt. But now we need to do it from 0 to infinity, and so we'll use the fundamental theorem of calculus. Hopefully I didn't make an error somewhere. I don't think so, though. So with the fundamental theorem of calculus, this really hurts my hand. With the fundamental theorem of calculus, we would do the f of b be the upper boundary minus f of a. And f, don't get confused, that's not the flow rate. That's just f as a function notation that is often used in calculus books. So f of b, our b is infinity, our a is 0. Basically, we're doing this from... Why can't... Sometimes I just blank, I'm drawing infinity. Infinity and 0. So if we were to plug in infinity everywhere we see a t, what do we get? We get... Let's see, we get negative infinity times e to the negative infinity. Negative times a negative is positive infinity. So let's say we do f of infinity is equal to infinity plus, let's see here, we got negative infinity, so we got positive infinity plus a negative infinity. If we plug an infinity here, we get negative infinity. Sorry about that. So I rewrote the notation for this portion to be plus 1 over 0.31 squared, so it's easier to look at. And so if we plug in infinity to our equation, we get infinity for this term. For this term, we also get infinity. And then for this term, we get negative infinity. So we get infinity, basically we just get infinity minus infinity, which the limit is close to 0, approaches 0. And then if we plug in 0, so our f of 0, we plug in 0 to this term, we get 0. We plug it in to this term, we get 0. So then we get 0.2 times this term right here, because if we plug in 0 into this term, we get 1. Yeah, we get 1, so we just get this. So we're really just left with 0.2 over 0.31 times 1 over 0.31 with the 0.31 squared. And so this is really equal to 0.2 over 0.31 cubed. And there you have it, our f of 0, which is what is important. So I'll go ahead and block this off. And so if we plug this into our original formula, remember this yellow guy over here, we get where we calculated 370 milliliters per degree Celsius. We get, so F is equal to 370 milliliters degrees Celsius divided by 0.2 over 0.31. I can write that better. 0.31 cubed, and this is in degrees Celsius seconds. And so if we cross out degrees Celsius, we get 370 divided by 0.2 divided by 0.31 cubed. And this is all in milliliters seconds. Milliliters per second. Milliliters per second. And this actually comes out to 0.1 milliliters per second. And if we convert this using a conversion calculator, we get roughly 3.3 liters per minute. And there you go. Our cardiac output is above 3 liters per minute, which is good, so they're not dying. It's a little low, as the normal rate is around 5. But that is how you do thermodilution using integral calculus, specifically integration by parts. And with that, we'll see you. Oh, before I go, actually, there's been a lot of clinical trials done regarding thermodilution catheterization, and none of them found that it improved mortality or hospital stay. In fact, it has been associated with even more complications. A meta-analysis found the same findings or similar findings, and collectively all of these studies have cast doubt on this invasive diagnostic approach. But I'm sure cardiologists do still use it. The jury's not out yet, because it's really just meant to measure cardiac output. It's not a treatment. It's just to provide the physician with additional information. and there hasn't been something better developed yet. So cardiologists are still using it, and I thought this was a good example to run through integration by parts. So with that, we'll see you in the next video.